Now, in this session, we are going to see Fermi factor and success of QFET in material science. What is a Fermi factor? Fermi factor, denoted by F of E, is the probability of occupation of a given energy state of a material at a given temperature T. That is, F of E is nothing but a probability of an electron occupying an energy state E. F of E is equal to 1 by e to the power of E minus EF by KT plus 1. What is this EF? Is the Fermi energy level. We will see in the successive sessions what is EF. K is the Boltzmann constant and T is the temperature. Now we will see the dependence of Fermi factor on temperature and effect of occupancy of energy levels. Now first we are going to see what are the temperatures at which this Fermi factor can determine the probability of an electron occupying an energy level E. Now, first condition, we say that probability of occupation for E less than EF at temperature T equals to 0 Kelvin. The probability is given by F of E is equal to, since E is less than EF, so what will happen? E to the power of minus infinity plus 1. How did you get minus infinity? Based on the F of E, the above equation, F of E is equal to 1 by e to the power of E minus EF by KT plus 1. So here, since E is less than EF, so the term and T equals to 0. So a negative quantity divided by T equals to 0 gives minus infinity plus 1, and e to the power of minus infinity is 0. So 1 by 0 plus 1, that is 1. That means the probability of an electron occupying an energy level E at T equals to 0, E is less than EF is 1, which implies the energy is 100% occupied for E less than EF. That means F of E, the probability is 1 means 100% occupancy will be there by an electron for energy levels E less than EF. This is very important concept. So at T equal to 0, all the energy levels below Fermi level are completely occupied. The second condition here we are going to see is the probability of occupation for E greater than EF at T equals to 0 Kelvin. F of E is equal to, taking the previous equation, F of E is equal to 1 by e to the power of E minus EF by KT plus 1. In that equation, if you substitute E greater than EF, so numerator becomes a positive quantity by 0 gives positive infinity. E to the power of positive infinity is nothing but infinity. So 1 by infinity is nothing but 0. Here F of E equals to 0 implies that none of the energy levels are occupied when E greater than EF at T equals to 0. Hence at T equals to 0, all energy levels above Fermi level are unoccupied. The third condition is probability of occupation at ordinary temperatures. At ordinary temperatures, though the probability remains 1 for E less than EF, it starts decreasing from 1 as the value of E becomes closer to EF as shown in the curve. Here from this curve you can see many things. Before going to that, we will see the expression when T greater than 0 at E is equal to EF. If you see here, F of E is equal to 1 by e to the power of 0 plus 1 because E is equal to EF and T greater than 0. So if you substitute the values E is equal to EF, the numerator becomes 0. So 0, e to the power of 0 plus 1, we know that e to the power of 0 plus 1 is 1. So 1 plus 1 is 2. So 1 by 2, that is 0.5. The occupancy is 0.5. So that means E is equal to EF is nothing but the Fermi energy level. When E equals to EF, this equation leads to F of E is equal to 0.5. Hence at E equals to EF, the probability of occupation is 0.5. From the diagram, you can see the values at T equals to 0, the probability is 1 for E less than EF, and as T is greater than 0, the probability is coming to 0.5. So here for E greater than EF, the probability falls off to 0. Next is success of quantum free electron theory. What is a specific heat? We have seen the failures of QFET. Now we will see the success of quantum free electron theory. Whatever the failures that we have seen in the QFET were successfully explained by the quantum free electron theory. First we will start with the specific heat, which was failure in the failure in QFET has become success in QFET. The specific heat. As per QFET, all the free electrons in the metal absorbs the heat energy when a metal is heated, results in a large value of specific heat. What exactly is specific heat? The amount of heat required to raise 1 gram of water through 1 degree centigrade. This is the specific heat. So when the heat has been given, all the free electrons are taken up the metal, absorb the heat. So large amount of heat is required to raise the value of specific heat. But as for QFET, only few electrons that are occupying energy levels close to Fermi level EF absorb the heat energy to get excited to higher energy levels and contribute for a specific heat. So the value of specific heat is small. So as per QFET, the specific heat of the solids is given by Cv is equal to 2K by EF into RT. If you substitute the values as EF is equal to 5 electron volts, as EF lies between 1 to 10 electron volts for metal, the above results agrees well with the experimental observed values. That means if you substitute EF value here, put the value of R, and if you substitute the value of Cv is equal to 2K by EF. K is the Boltzmann constant. If you substitute the value of EF here, it is approximately coming to Cv is equal to 10 to the power of minus 4 RT, which was in agreement with the experimental results. Therefore, Cv is equal to 10 to the power of minus 4 RT. So, experimental results are in agreement with the theoretical result. So, this is a success. Next is temperature dependence of electrical conductivity. As per QFET, electrical conductivity for metal is sigma is equal to Ne square lambda by m star into Vf. This is equation 1. Now, Ef and Vf are independent of temperature and dependence of lambda as shown below. The vibrations of larger area of cross section scatter more effectively, thereby reducing lambda. What is lambda? Lambda is nothing but mean free path, which I have already given the definitions and explained in the previous sections. So, lambda is nothing but the mean free path. Mean free path. The distance travelled by the electrons between two successive collisions is called mean free path. More the collisions, mean free path reduces. Therefore, lambda is proportional to 1 by pi r square. But the energy E of a vibrating body is proportional to the square of the amplitude, and E is due to thermal energy and E is proportional to temperature. Based on these three assumptions, or we know that these are the things that are happening, the energy E and dependency on T, we write it as R square is proportional to T, where R is nothing but the square of the amplitude. That is from the equation 2. Therefore, from equation 2, lambda is proportional to 1 by T. See, these three A, B and C, the energy of a vibrating body is proportional to square of the amplitude, and E is due to thermal energy and E is proportional to temperature. From these three equations, we have contributed as R square is proportional to T. But from equation 2, we know that R square is proportional to 1 by lambda. So, we are substituting that over into this equation, lambda. Instead of R square, we are putting as 1 by lambda, or taking the cross multiplication, we are putting as lambda is proportional to 1 by T, which is equation 3. So, comparing 1 and 3, what we can say that sigma is proportional to 1 by T. What does equation 1 say? Sigma is proportional to lambda, but here lambda is proportional to 1 by T. Therefore, sigma is proportional to 1 by T. Thus, the dependence of conductivity on temperature is correctly explained. So, this is another success of QFET. Next, the third success is electrical conductivity and electron concentration. As per quantum free electron theory, sigma is proportional to Ne square lambda by m star into Vf. Thus, the conductivity depends on N ratio lambda by Vf and m star. If we compare the case of copper and aluminium, the value of N for aluminium is 2.13 times greater than that of copper, but the value of lambda by Vf for copper is 3.73 times higher than that of aluminium. Therefore, sigma for copper is greater than sigma for aluminium. Also, m star for aluminium is 1.08 times greater than that of copper. Due to inverse dependence of sigma on m star, thus the conductivity of aluminium is less than that of copper. Here the major difference comes is sigma not only depends on N, the ratio lambda by Vf also contributes to conductivity. M star also depends on conductivity. So M star is inversely proportional to conductivity and the ratio lambda by Vf also gives rise to contribution to the conductivity. Therefore, whatever the explanation given by QFET was successfully in agreement with the experimental values. These three are the success of QFET. Thank you.